Okay, so let's look at another type of indeterminate problem. So this is the one where we have a composite shaft. So it has a steel core in the middle and an aluminum jacket. Steel core has a modulus rigidity of 77 gigapascals and is 54 millimeters in diameter. The shaft the jacket, the aluminum jacket, its modulus rigidity is 27 gigapascals, and its outer diameter is 72 millimeters. And then the torque at the end that's applied, that's 4 kilonewton meters. So we want to find out what the maximum shearing stress is in both the core and the jacket, and then the angle of twist. So, going over here. So again, I like to put my walls at the x origin. X-axis goes this way. It's a 25-meter long section. And again, so I just restating the values that we had, restating our problem. So our compatibility condition here is that these things are bonded together so they twist at the same rate. So the angle of twist at the end is the same, and in fact the angle of twist, if you take any section, needs to be the same. There's no slipping between these two. So if that's going to happen, then basically some portion of the torque is going to be kind of carried by the aluminum on the outside, and some portion of the torque is going to be carried by the steel on the inside. So we know that we can kind of add those two things together, and they will result in the 4 kilonewton meters that we are applying to it. So the torque in the steel and the torque in the aluminum. And again, our known is that the twist is the same. So if we want to analyze this, we're going to need to know what the J's are. So for the steel, pi over 2 times the radius to the fourth. So again, keep in mind, don't plug into your diameter there, plug in your radius. So 27 millimeters to the fourth gives us this. What is it? 834.8 times 10 to the 3 millimeters to the fourth. Got our J for the aluminum. So again, pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. So 32 millimeters to the fourth minus 27 millimeters to the fourth gives us 1,803 times 10 to the 3 millimeters to the fourth. Again, I just kept that in terms of 10 to the 3 because I used this one 10 to the 3, and I'm going to cancel them out later. So we've got the we got this formula here that those two are related. So again, torque in the steel times the length divided by G for the steel times J for the steel is going to be equal to the torque in the aluminum times the length divided by the G for the aluminum and the J for the aluminum. So the lengths cancel out, obviously. Same length for both. And we are left with, we're able to kind of solve for the torque in the steel in terms of the torque of the aluminum. That's just going to be the torque in the aluminum times the ratio between the G for the steel divided by the G for the aluminum times the J for the steel divided by the J for the aluminum. So that's going to be 77 divided by 27 gigapascals over gigapascals, and 834.8 divided by 1,803 times 10 to the 3 millimeters to the fourth divided by, the 10. These cancel out, these cancel out. And that gives us 1.32 torque of the aluminum. So the steel's carrying more of the load than the aluminum is. which isn't too surprising, I guess. It's stiffer and there's more of it. So the torque for the steel plus the torque for the aluminum needs to equal the 4 kilonewton meters, and that's not a square sign, that's supposed to be an equal sign there. So that's equal to 1.32 plus 1 bracket bracket times the torque in the aluminum is equal to the 4. So our torque in the aluminum, 4 divided by 2.32, is equal to 1.72 kilonewton meters, which means that the torque in the steel is whatever's left. So that's 4 minus the 1.72 gives us the 2.28 kilonewton meters. So from there, so we know the torque in the steel, we know the torque in the aluminum. We can figure out what the twist would be. We know that the twist is the same in both of them, so we can use either equation to solve for the twist. So I'm going to use the steel one. So again, torque in the steel times the length, 25 meters, divided by the G for the steel and the J for the steel. And if I just plug in that in, blindly, again, I kind of want to emphasize why I like to do my conversion to decent units beforehand. Just plugging that in blindly, we got 8.867 times 10 to the negative 7 kilonewton meters squared divided by GPa millimeters to the 4th. So if we want to get this into something useful, so I convert the the newtons, the kilonewtons into newtons by multiplying by 1,000, the meters into millimeters, so multiply that by 1,000, and again keep in mind the square here as well, so that 1,000 gets squared. Then the gigapascals I convert into 1,000 newtons per millimeter squared. Again, gigapascals and megapascal. Megapascal is a newton per millimeter squared. And then the millimeters to the 4th, cancel out 2 of them for that, cancel out the other 2 for that. And then, one of these thousands cancels out, so we're just left multiplying this 8.867 times 10 to the negative 7 by 1,000 twice, so 10 to the 6, brings us back up to 0.887 radians, or 50.8 degrees, which is a fair amount of twist, but it's over 25 meter section, so that's reasonable at least. So we got that. We've also got, we can also calculate what the stress levels are. So again, stress level is going to be equal to the torque times the radius divided by the J. So again, torque in the steel in newton millimeters, because again I want to keep everything nice and simple when I do these calculations. Times 27 millimeters divided by our J here, 834.8 times 10 to the 3 millimeters to the 4th. So again, millimeters cancels out 2 of our millimeters to the 4th, leaving us with Newton per millimeters as our unit, which is megapascals. Same deal with our aluminum. Just multiplying everything together. The 1,720 Newton millimeters times 36 millimeters divided by 1,803 times 10 to the 3 millimeters to the 4th. Everything cancels out nicely to newtons, newtons per millimeter squared. And there we go. 34.3 megapascals. And that's how you do those composite torsion problems.